what is the expectation of the Poisson distribution. We know that probability expectation of a random variable is summation over x into probability x equal to x over all values x take. In a Poisson distribution, x takes value from 0 to infinity. So, this is summation x going from 0 to infinity x into e to the minus lambda, lambda to the power of x by x factorial. Now, I can rewrite this term as summation x going from 0 to infinity x e to the minus lambda. I retain it because it is independent of x. The denominator I am going to write x factorial is x into x minus 1 factorial, and the numerator I am going to write it as lambda to the power of x raised to the power of x. I am going to write it as lambda into lambda raised to x minus 1. So, now I can cancel out these two terms. I get summation x going from 0 to infinity e to the minus lambda into lambda, lambda to the x minus 1 by x minus 1 factorial. Now, these two terms are independent of x, so I can write it as lambda e to the power of minus lambda. I get a summation x going from 0 to infinity lambda to the power of x minus 1 by x minus 1 factorial. If I expand the term here, I get it as lambda e to the power of minus lambda into x equal to 0. I can write this x. So, x equal to 0, this would be an x equal to 1 to infinity, because x equal to 0 would. So, this is x, I get an x into x minus 1 factorial. So, when x equal to lambda into lambda to the power of x minus 1, I can write this as x equal to 1 to infinity. So, I get a lambda to the power of 0 by 0 factorial by lambda 1 by 1 factorial, and or I can take x minus 1 equal to y. If x minus 1 equal to y, I get a y equal to 0 to infinity lambda to the power of y by y factorial, which I know that this term is nothing but e to the power of lambda. I get lambda into e to the power of minus lambda into e to the power of lambda. These two would be just 1, and I get it as lambda. So, my expected value of a Poisson distribution with parameter lambda is lambda itself. And that is what we saw as the average, if you remember, in the example that we took. So, expectation or expected value of x is going to be just lambda. Now, how do we compute the variance of x? Recall, the variance of x is expectation of x square minus expectation of x whole square. This is something which we already know. Now, to compute expectation of x square, I want to compute expectation of x into x minus 1. Now, if I compute expectation of x into x minus 1, that is nothing but summation x going from 0 to infinity x into x minus 1 into probability of x equal to x, which is e to the power of minus lambda, lambda to the power of x by x factorial. Now, I can write this denominator as x into x minus 1 into x minus 2 factorial, and I can write this lambda to the power of x as lambda square into lambda raised to x minus 2. So, just as what we did before, I can write this as x when x equal to 0 to infinity. Now, I have x going from 1 to 0. So, I remove this lambda square and e to the power of minus lambda here, and I can just check that this becomes lambda to the power of x minus 2 by x minus 2 factorial, x going from 2 to infinity, and we can again check that this is nothing but e to the power of lambda, which will give me lambda square e to the power of minus lambda into e to the power of lambda. This product equal to 1, which will give me that expectation of x into x minus 1 is lambda square. If expectation of x into x minus 1 is going to be lambda square, the left hand side tells me that expectation of x into x minus 1 is expectation of x square minus expectation of x, which is equal to lambda square. I get expectation of x square is going to be lambda square plus lambda. Now, variance of x is expectation of x square minus expectation of x whole square. From 1 I get expectation of x square is lambda square plus lambda. I already know the expectation of x is lambda square, lambda. So, expectation of x whole square is lambda square, which gives me that the variance of x is also equal to lambda. Hence, the variance of a Poisson distribution is also equal to lambda. So, a Poisson distribution has both the expected value and the variance to be the same. And if I say that x is a Poisson variable with parameter lambda, both the expected value and the variance of x are equal to lambda. What does this imply for us? Suppose I get a discrete distribution which exhibit the same mean and the variance, then I can perhaps think of modeling it as a Poisson distribution, and that's something which we saw in our example, when we derived the mass function, that from the observation we saw that this exactly what we saw in the example was the mean was 2.39 and the variance was 2.16, which are almost close to each other. So, that is how we can say that a Poisson distribution seems to, so that is how we can see that a Poisson distribution is a good distribution to model events which have the same mean and variance, discrete distribution where you are doing a count. Now, we are going to look at a few applications of Poisson distribution that arise in our daily life. Let's look at a few examples that arise in a fixed interval of time. This could be number of vehicles. We have already seen this example earlier, number of vehicles passing through a traffic intersection in a period of time, fixed interval of time. Number of people withdrawing money from a bank in a fixed interval of time. The fixed interval could be 15 minutes, or number of telephone calls received per minute at a call center. All of this are number of events happening in an interval of time. Now, some of the events that occur in an interval of space is number of typos or incorrect spelling or spelling mistakes that occur in a book, number of defects in a cable or a wire of finite length. Again, the interval here is the finite length. In the earlier case of a book, it was a book, which is again a space. Number of defects per meter in a roll of cloth. So, all these are examples, and we can model each one of these examples as a Poisson distribution. Now, let's look at a few examples where we are modeling in time. So, suppose the number of accidents per week in a factory is modeled as a Poisson distribution which a mean of 0.5. I know the parameter is going to be 0.5 because the mean of a Poisson distribution is nothing but lambda. I am interested in knowing what is the probability that in a particular week there would be at most 2 incidents. So, I know x is a Poisson with parameter lambda equal to 0.5. The question I am asking is what would it be at most 2 accidents, that is probability x is less than or equal to 2. Now, probability x is less than or equal to 2 is probability x equal to 0 plus probability x equal to 1 plus probability x is equal to 2. Probability x equal to 0 is e to the power of minus 0.5, 0.5 to the power of 0 by 0 factorial, e to the minus 1, 0.5, 0.5 to the 1 by 1 factorial, e to the 0.5, 0.5 to the power of 2 by 2 factorial. And you can see that that value is summation of this, which is 0.9856. Now, suppose we are again, let's look at another example where the number of dogs that are killed on a particular stretch of road in Chennai on any one day. So, the time interval here is on any one day. I know it can be modeled as a Poisson 0.42. So, lambda is 0.42. x, which is the number of dogs that are killed on any one day, I know this is a Poisson with lambda equal to 0.12. So, the first question is asking probability x is exactly equal to 2. I know that is going to be e to the minus 0.42, 0.42 to the raised to 2 by 2 factorial, and that value I know is 0.058. The next question is find the probability that exactly 2 dogs are killed over a 5-day period. If I know that 0.42, this 0.42 says that on an average 0.42 dogs are killed on a day. That's what this 0.42, because lambda is the average. On a day, if 0.42 is the average number of dogs killed in a day, what is the average number of dogs killed in 5-day period? It is going to be 0. This is going to be 1. So, it is going to be 2.1. So, if I have to model, I want to know what is the probability of x equal to 2 here. I need to know what is the parameter that is observed here, and this lambda over a 5-day period is going to be lambda equal to 2.1. I repeat, for 1 day it is 0.542. I know that it is independent, so I can find out what is the probability over what is the average over 5 days. I get that to be 2.1. So, I know that the x in this case is a probability with parameter 2.1, and if I want to calculate probability x equal to 2, it is e to the minus 2.1 into 2.1 raised to 2 by 2 factorial. We can verify that that value is 0.27. It's quite evident that the probability of 2 dogs killed over a 5-day period is going to be higher than probability of 2 dogs killed in a 1-day period. But I am using for both the cases, we are modeling it as a Poisson distribution. Now, let us look at a few examples where we are modeling it over space. Suppose a number of defects in a wire cable. So, here I have a cable, the length or the interval of the cable is a meter. I am saying lambda equal to 0.5 per meter, average of 0.5 per meter. So, x, which is the number of defects in a wire cable of 1 meter, can be modeled as a Poisson with lambda equal to 0.5, and the probability it will have exactly 3. A single meter will have exactly 3 defects is going to be e to the minus 0.5, 0.5 raised to 3 by 3 factorial. I identify the parameter of the distribution and I get probability x equal to 3 is e to the minus 0.5, 0.5 to the power of 3 by 3 factorial, which is 0.0126. Now, suppose I have another example where a typist makes 1500 mistakes in a book of 500 pages. Now, x is the number of mistakes per page. So, the interval I am talking here is an interval of space, and this I am interested in knowing what is the parameter of interest here. I have 1500 mistakes in 500 pages. So, in one page I have how many mistakes? So, by cross multiplication I know it is going to be 1500 by 500, which is equal to 3. So, the average number of mistakes in a page is going to be 3. So, if x is the number of mistakes in a page, then I know that x is a Poisson with parameter lambda equal to 3. And how did I get this 3? I know 1500 and 500 pages. So, in one page I know it is 1500 by 500, which is 3. On how many pages would you expect to find no mistakes? So, this translates to probability x is the number of mistakes in a page. Number of mistakes probability x equal to 0 is e to the minus lambda, where lambda is 3. 3 raised to 0 by 0 factorial, which is just e to the minus 3. So, this is the probability of finding no mistake in one page. I have 500 pages. So, 500 into e to the power of minus 3 would give me the number of pages with no mistakes. Similarly, on how many pages will I expect one mistake? That would be e to the power of minus 1, 3 to the power of 1 by 1 factorial. 500 into e to the power of minus 1 into 3 to the power of 1 by 1 factorial, or 3 times e to the power of 1 would give me the number of pages with one mistake. Similarly, I can with I mistakes, number of pages with I mistakes would be 500 into e to the power of I, 3 to the power of I by I factorial will give the number of pages in the book with I mistakes. So, in summary, what we have seen here is we have seen how we can model the applications or situations that arise in our day-to-day life, both number of events in an interval of time and an interval of space using the Poisson distribution.